So I will share the screen to start. And the chapter 7 slides, I updated some slides so that if you can download the if you want to see it. You know, just minor updates. So probably if you have already printed out, that's fine. But if you want to use the electronic copy, then you can use the latest one. Okay, so I will share the screen. Just a moment. Okay, so last time we discussed one-way ANOVA. So one-way ANOVA is a generalization of t-test. So t-test has only two groups to compare, but in ANOVA, one-way layout, generally that we have I groups. So I maybe 2, maybe 3, maybe larger than 3. And we test if all groups have the same mean or some groups have different means. So that is one-way layout or one-way ANOVA. One-way layout may be the name for the model, and the one-way ANOVA is the entire scheme of testing. And today's topic is two-way ANOVA. I think that sorry. Yeah, two-way ANOVA. So in two-way ANOVA, it's a further generalization, further extension of one-way ANOVA. So we have the two factors to explain the real valued variable. For example, one factor may be the blood type, and another factor is blood type and maybe gender. And to explain, I don't know, average age of those people. And so the response variable is a real valued variable. So not only we have multiple groups, but we have two factors. Maybe we have 4 blood types and 2 genders. Yeah, and here an example is the yield of plant X may depends on the fertilizer, maybe type of the fertilizer and the type of cultivation, either ground or a greenhouse. So we have two factors. So for this kind of data, the analysis is called the two-way analysis of variance or two-way ANOVA. So this model tests the overall effect of each factor, whether fertilizer makes difference and also whether type of cultivation makes difference. So maybe we have multiple fertilizers, so we have something similar to the one-way ANOVA. So the model is here, so two-way layout. So consider a simple situation that we have the m times n measurement, xij, and I is equal to 1 to m, and j is equal to 1 to n. And the xij is the value of the response variable. So this belongs to the ith group of the factor 1, so ith fertilizer, and the jth group of the factor 2. So j is equal to either 1 or 2. 1 is ground and 2 is greenhouse. So I and j that determines the condition for that crop. And our model is xij is equal to mu plus alpha I plus beta j plus error epsilon ij. Here epsilon ij is IID, normal, 0 sigma square. So basically so the xij is measurements. So this is the yield of the crop. So we have overall level of the overall mean level of measurements. That is mu. And the alpha I is the factor determined by the fertilizer. So so maybe alpha 1 is the base level, and if the fertilizer 2 makes more crops, then basically alpha 2 is a positive number. So it adjusts the yield level by fertilizer. And the beta j represents the factor determined by the cultivation, so either ground or greenhouse. If the beta 1 is the ground, the j is equal to 1 is the baseline, the beta 1 is 0, and the beta 2 represents the difference between the greenhouse and the ground. So the additional, maybe the yield compared to ground for the greenhouse. So usually we assume the alpha 1 is equal to 0 and the beta 1 is equal to 0. The two make the first group as the baseline. And some people make slightly different assumptions, such as summation of alpha I is 0 and summation of beta j is 0. Sorry, I made a big mistake to explain mu. So mu is overall. So in this case, the mu is overall mean. Mean yield. But for the first assumption, actually the mu is the baseline yield. For I is equal to 1 and j is equal to 1. So basically, so this is the yield for the first fertilizer and on the ground. And how R determines the order of alpha i's? Actually, the R determines alpha I in alphabetical order in default. So to change, actually, we have to modify the original factor vector. Factor vector into different order by option levels. So you can modify the vector itself, the factor vector itself, by the levels option. So when you define a vector, that you can manipulate the order. And my recommendation is to make the largest group as the baseline. Usually that is the easiest to interpret. For example, if we have the maybe individual, the data for individuals, and the race is a factor, and that is US data, and we have white and African American, and maybe the Latino or the Asian and Pacific Islander, and maybe others or something like that. And for example, think about the case that others is a baseline. That is really hard to interpret, right? So because when we estimate parameter for white, for example, that is the difference between white and others. But others probably have very small group, so it's hard to interpret. So probably the two make the largest group as the baseline makes more sense. So that is my recommendation. So no, uniform rule for that, but if others is a baseline, or if the Asian becomes baseline because it starts with A, but that is very small group, so probably that is harder to interpret. Okay, so we have similar notions to the one-way ANOVA. So we calculate the sum of squared deviations for the first factor, 1, SSD1, and second factor, SSD2, and SSD residual we have. Okay, so at first we define the X bar I dot. This is the group mean of the ice group for the first factor. So group the ice, so the mean of ice level of first factor. And this is the mean of the J's level of the second factor. And this is overall mean. So SSD1 is SSD1 basically describes the how much variability in between groups in factor 1. So we have deviation of ice group from the overall mean. So if we take the square of this and take summation, basically this means the variability between groups for first factor. So variability between groups for first factor. And the second one, SSD2 is similar, variability between groups for the second factor. And SSD rest, this is basically the variability after accounting for the two factors. So variability after accounting for two factors. First and second factor. So actually, yeah, this is a little bit hard to interpret, but this is basically xij minus x dot dot bar minus the xi dot bar minus x dot dot bar minus xj. So xi, x dot j bar minus x bar dot dot. So basically, the first term is deviation of xij from the overall mean. So this is deviation of the ice group from the overall mean. So, and this is the deviation of the J's group of the second factor from the overall mean. So basically we have deviation, and after adjusting the fact that the observation is in group I for the first factor, group J for the second factor, that we get this. So this is the after adjustment, we have some intrinsic error. So that is the term in SSD residual. So basically, if SSD1 is large compared to compared to intrinsic error, then we decide that the first factor matters for this xij's. And if SSD2 is large compared to the size of intrinsic errors, then we can say the second factor matters for these xij's. And based on these three quantities that we can test null hypothesis. And these are the tests that ANOVA does. So yeah, we have several different ways to do ANOVA, but this is the most common setting. So we have the factor alpha I and the factor beta j. And the first test is that we test this null hypothesis against this alternative. Yeah, so basically the baseline is the just xij is equal to mu plus epsilon ij. So nothing explains xij. And alternative hypothesis is the first factor matters. First factor has some information that in addition to the null model. And the second test we will do is this null hypothesis H02 against H12. So H0 is the model with mu and alpha I. So the first factor matters for xij. And the alternative, I mean the alpha i's may be 0. So the first factor may matter the xij. And alternative hypothesis is even accounting for the first factor, information, the second factor has additional information to explain Xij. So this is the alternative hypothesis. So the test is sequential. So the first test is the baseline, so null model against the model with alpha j. But the second alpha I, but the second test is the model with alpha I and model with alpha I and beta j. So this is sequential test. So actually, so because of this structure, the order of two factors matter for the test. So whether you put alpha I first or beta j first, that matter. However, that when each pair ij has the same number of observations, the one in our case, so we have the one observation for each pair of, the fertilizer and the cultivation, then actually the test result is invariant when order is changed. So yeah, so this is a kind of the lucky case, but so in this case, the second test can be also interpreted as just xij is equal to mu plus epsilon ij against the xij is equal to mu plus beta j plus epsilon ij. Yeah. So yeah, but later we discuss more general model, and in that model, if we have the different number of the observations for each ij, each pair of ij's, then this order actually matters. Questions? So, okay, so then the theorem. So how to test? So I mentioned that if SSD1 is relatively large, then factor 1 matters. So it's natural that we use basically the ratio SSD1 divided by SSD residual, the size of intrinsic error. Then if this ratio adjusted by some degrees of freedom, this statistic follows this F distribution under null hypothesis. So yeah, and if F superscript 1 is large, then we reject a null hypothesis to say the factor 1 matters. So the rejection region is F superscript 1 is larger than some threshold. If significance level is 5%, then we use the 95th percentile of this F distribution. So suppose that we have maybe 4 groups, then we have M is equal to 4. And for each group, we have 10 observations, N is equal to 10. Then this F statistic follows the degrees of freedom. 3 is 4 minus 1, and the 4 minus 1 times 10 minus 1. So that is the 3 times 9. So F of 3, 27. Then we make a distribution of F. So this is the PDF, probability density function of F3, 27. Then rejection region is here. So F of 0.95 given this degrees of freedom. So this is 5% of the area. So this is alpha. Then the rejection region is here. Or if you want to calculate p-value of observed F statistic, I would say F hat, and then this area is p-value. So we will have one quiz question to answer this p-value based on these numbers, SSD1, SSD residual. So you are given these numbers, but you have to manually calculate the F value. Then also you have to calculate this area. You can use the PF function to calculate this area. So this is the PF of F hat. You have to specify degrees of freedom, but that is today's first quiz. Any question? Okay, good. And the next one. So this is almost the same. So how to test the second alternative hypothesis? Sorry, the second hypothesis. Then we compare SSD2 and SSD residual. So basically, the second factor have n groups. So here n minus 1. And the residual, SSD residual, we divide by this m minus 1 times n minus 1. And again, if this F superscript 2 is large enough, then we reject H naught. So to summarize, the ANOVA table that looks like this. So predictor 1, predictor 2, and we have degrees of freedom here. If we have 4 groups, then m minus 1, so df is 3. And the 10 groups for predictor 2, we have this is 9. Yep. And this is good to check because when our outputs, then if these numbers are different from you expected, then probably your code has some error. So typical error is, okay, so df comes 1 and 9. Why 1? Because probably the predictor 1 is recognized as a continuous variable. So if this is a continuous variable, then even if the values are 1, 1, 1, 2, 2, 2, 3, 3, 3, or something like that, they are recognize this as continuous variable. So actually it is just one variable, not 3 levels. So in such a case, that this m minus 1 becomes 1. So just make sure that these numbers are the number of groups minus 1. Then SSD1 and SSD2 SSD residual is calculated based on the formula in the previous slide. And then we divide this by degrees of freedom to get this, the MS, the mean squared deviation. And then we compare this with this to get this F value. And based on the PF function, the probability density function of F, we can calculate P value. The same for predictor 2. Any questions? Okay. And example 1, the air passengers data. So this is the default. In default, our package and includes the 144, the monthly numbers of international air passengers. And this is a little confusing, but this is not really a matrix, and it's not a table either. And this is time series object. So actually, this is technically a vector with 144 elements. So vector with specific feature. So, but it has information of frequency and the time index. So this vector is defined so that it start at January 1949 and the monthly data. So actually, I'll put this in this way, but actually this is a vector with 144 elements. But anyway, so we want to use these as 2 factors. The one is months, and another factor is year. So different years have different level of air passengers, maybe some increasing trend, but not necessarily just linear trend, but for some specific years, we may have larger number of passengers. Maybe in the year of Olympics, maybe the level is higher, or maybe some specific events makes it larger, numbers larger or small. And also it should have some seasonality. So you can see around maybe July, August, maybe we have the larger number of passengers, and we have smaller number of passengers in February, for example. So we have seasonality. So that can be expressed by the months as factor. And okay, so just as a toy example that we select these 5 years, if we use every years, then actually it's almost obvious that we have more passengers in 1960 than 1949. So we just use these 5 years of data. Sorry, why this happens. So just 5 years. So first 5 years of data, we use this. And we set alpha I as year and the beta j as month. And we want to see if these are significant factors. So we have to create the factor vectors representing year and representing month. So if the air passengers object is a matrix, then probably it's easy. So just we can generate some rows and columns or something, but we have to actually generate vectors. So first 12 elements are 1949, next 12 elements are 1950, and so on. And this is not numeric, just we want to make each of these 5 years as a factor. So I put as dot factor function here. And month also the same. So we repeat 1 to 12 5 times, but we make it as a factor. And then we make a data frame. So first series is passenger, and next is year or passenger. Yep, we just confine the data set into the first 60 observations. So we make this one. Yeah, time series object becomes the just usual vector if you select the subset of observations, subset of the time series vector. So it's a little bit confusing. And we make a data frame consisting of passenger, year, and month. So this is necessary format to fit the ANOVA models. So the data looks like this, the number of passengers here and year and month here. Then we can use the linear model. So passenger tilde year plus month. Then we can do this ANOVA. And if you put the ANOVA, this object LM within this ANOVA function, then we get this table. I think I got one question. Is the passenger variable initially an empty data frame to fill data with later on? The passenger variable is initially defined as the first 60 observations of air passengers. So initially defined as a vector with 60 elements. But of course, you can, if you would like, that you can create an empty vector and that you can plug in numbers. Yeah, I think probably that question is very logical. So probably you have to declare the vector with specific form. But in R is not that rigorous language. So either you can create an empty vector or directly define the first 60 observations. Second question from another student. Are the headers on the sides and the tops automatically not included in 1 to 60? I guess so. So once you select the subset of time series, the all frequency and the time index information has been lost. So we have to use more specific function to keep those information. I think that we have some window function in time series object to make it. So yeah, actually this passenger object is just a vector of 60 elements. And this is ANOVA result. So you can see that degrees of freedom for year is 4 because we have 5 years. So 5 factors, and the degrees of freedom is 5 minus 1. And the months we have 11, so 12 minus 1. So it sounds fine. And sum of squared deviations. So you can interpret these numbers. So basically in total, we have about a variation of 101,000. And that variation is, maybe just to make it simple, this is around the 100,000. So we assume the total is around this. Then basically, 78% of deviations, squared deviations, is explained by year. So if you know the year of the observation, then you can determine 78% of the variability. And another 22%, 21.7% is explained by month. So basically the air passenger, monthly air passenger is mostly explained by year, but partially explained by the seasonality, monthly seasonality. And the residual is pretty small, but still the 2,700. So about 3% of the variation between months remains as intrinsic error. And you can see this number. This number is just the 78,450 divided by 4. So 19,000. And you can do this for this one and also this one. So residual, that we have the degrees of freedom of m-1 times n-1. And you can calculate this. Then this F statistic is the ratio of these two numbers. So this is the ratio of these two numbers. And based on F value, we can calculate this. So F value is very roughly speaking around 1. Okay. F value is chi-square n over chi-square. Maybe nm is not really misleading. So chi k square over k and chi l square over l, or something like that. And the numerator and the denominator, so each of these has expectation of 1. So expectation of numerator is 1, denominator is also 1. So that means this does not mean the expectation of entire quantity is equal to 1, but this is around 1. So 311 is extremely a large number. So we expect the null hypothesis is rejected. Actually, the 78% of variation is explained by year. So it's very natural that the year is a significant factor to explain the number of air passengers. Okay, so now that we stop for a while and decide the final presentation dates. And I will share the screen. And I got just one request from a student who cannot attend today's lecture. And she's a Wayne State University athlete, and there's some competition on one of those days. So that's entirely reasonable request to pick the date. Yeah, okay, so now I think you see screen. Okay, so first, so we have 3 possible dates for presentation. Maybe I have to make it larger. And on the last day, this is during the final exam period. That is the 6:30 to 8:30. So we have a slightly longer lecture time. And we need maybe 5 presentations on the December 5th and 7th, and maybe 8 presentations on 14th. And also video presentations, I make it due on these 3 dates, and I upload the video to not upload, but I would ask you to upload video to your Google Drive or YouTube channel, and that so that everyone can see it. And I will ask you to submit final project plan, and I will make comments in the order of these presentations. So that means that if your presentation is December 7th, for example, 14th, that does not mean you have 1 more week to do. Okay, so I will comment in the same order as these presentations. And yeah, so it really depends on your preference, but actually the earlier dates, successful rate is higher in the past because the many students are busier in the end of the semester. Okay, so anyone have any requests? Maybe you can turn on mic and you can say your name and which date you prefer. Maybe anyone, yeah, maybe December 5th. Anyone prefers December 5th? Maybe later we can make some of the presentation as video. So just maybe total is 6 or 7.
This is Jordan Ribby. I can go on the 5th.
5th. Sorry. Name again?
Jordan Ribby.
Jordan. Okay.
Yeah.
So total is. Sorry. Mick
Winborn, 1214.
Okay.
Nadia 1214.
Can Jason go on the 7th?
Sonali on the
Sorry,
7th.
Jason Moses, right?
Oh, yep.
Yeah, we have
Thanks.
2 Jasons. Yeah.
Oh, wow.
Sonali Sadapati on the 7th.
Sonali.
Vindhya, I can go on the 7th as well.
India.
Alexander, December 7th.
Alex.
Ryan, December 7th.
Ryan. Does anyone can do for on the first day?
Grant, I can do December 5th.
Okay, that's great. Yeah. You're a graduate student, right? Yeah, I think it's good to see some good presentation on the first day. So yeah, that's very good idea. Yeah, good. And others?
I three.
Go ahead.
Sorry, I three. I can go on the 7th.
Maitri. Sorry. YEE. Yep. And maybe I need I. Yep. Others? Andrea.
Parcel.
Oh, sorry. The parser.
I can go on the
parser.
5th.
Can you go 5th? No.
I can.
You can. Okay.
Yeah.
I think you asked many good.
I can also go on the 5th.
Oh, okay.
Yes.
Okay. Others?
Good job.
Sorry. Others maybe Dalver.
I can go on the 5th, Professor.
Okay, great.
This is Jose. I'll do 1214.
Sorry, Jose.
Yeah,
yeah.
Jose Jones. Spelled the H.
Sorry, the H. Jose. CA. Sorry. Yeah. And let me see how many people here. Oh, I got one request in chat. Maybe is a oh sorry. Just a moment. I can go on 5th. Jason. Yeah, sure. Go ahead. Yeah.
I'm available any of the days.
Okay. So maybe it's okay. Maybe I put as the, and maybe I put the Lex on 5th because she requested is a 5th or 7th, and 3, 6. Okay, so 6, and Mick and maybe Neil on the last day.
Okay, that works.
Okay, and how many students here? So we have the 18 participants, and one is me, one is my iPad. So we have 16 students, and the one request already received. So 17. So 6, 6, 4. Maybe one person didn't say anything. Maybe.
Professor, there's someone in the chat that mentioned they want to go the 14th.
Oh, sorry about that. Ada. 14th. Yeah. This is it. So everyone answered. Okay, so Nadir included, and Jose, Dalver, Andrea, Neil, Mate Parser, Jordan, Ryan, yes, and Mick Grant, and Alex, Sonali, others. Okay, then probably that's it. So I think some students didn't attend, but I put some. Oh, you spell. Oh, sorry about that. AK Alex. Oh, sorry. Alexander. Yep. Okay. So yeah. Okay. So I think that these are done, and I will schedule other students on either 5th, 7th, or 14th. Okay, great. I will send this schedule, but just make sure that you didn't make mistake. Once we decided, it's very hard to change the schedule. So yeah, you can exchange from another classmate, that's fine, but often no one agrees to exchange dates. Okay, so is that good? Okay. Okay, so now we continue the class. Any questions about presentation dates? Or hopefully I will comment all of your final project plan the 2 weeks before your final presentation date. Yeah, so the next topic is two-way analysis of variance with interaction. So we have thought about the model, the xij is equal to mu plus alpha I plus beta j plus epsilon ij. So this is entirely reasonable model. So the first factor matters for xij, and the second factor also matters for xij. But not necessarily the two factors matters as a linear combination, right? So for example, the greenhouse is combined with a specific fertilizer, then yield the skyrockets, not just a linear effect, but it's even larger effect, or maybe smaller effect if something is grown up in a greenhouse, then fertilizer does not matter, or something like that. So the effect is not necessarily additive. So not just alpha I plus beta j. So in general, we can think about the xij is equal to mu plus alpha I plus beta j plus gamma ij plus epsilon ij. So if we don't have this gamma ij, we have a kind of strong assumption that the volume of yield is linear combination of two factors, or in the previous example, volume of passengers is a linear function of year and mass. Yeah, so for the example of the passengers, that means we assume that the seasonal pattern is the same for all years. So, but that may not be true. If some years have Olympics in August, then for those specific years, August number should be higher than other months. I mean, relatively much larger than other months compared to other years. So if such an assumption does not hold, then we have to think about this a kind of full model. So this gamma ij is called interaction. But this does not really make sense. So xij is explained by the mu ij plus epsilon ij. And if such model is allowed, we can define xij is equal to mu ij. So estimate for mu ij is equal to xij. And then error becomes 0. So it does not make any sense. But this makes sense if we have multiple measurements for specific pair ij. So maybe this air passengers data maybe not really the case, but think about the fertilizer and the cultivation data. Then it's possible that maybe the 3 crops are, the 3 plants are grown up in the same condition. So 3 plants each are, grown up in the pair of conditions. So in such a case, we have multiple measurements for specific pair ij. So we can say that we have x sub ij1 and x sub ij2 and x sub ij3. So in such a case, this model makes total sense. So mu ij plus epsilon ijk. So we have the overall level for pair of ij, but the specific plant has some specific error. So mu ij plus epsilon ijk. So that is possible. So yeah, and we study this interaction, the model with interaction. And yeah, actually we go back a little bit and we go back to the air passenger data. And even if we don't really have the multiple observations for each pair ij, there's still that we can make this interaction plot. So this is just actually the 1 observation each for each point, but this x-axis is month, and the different lines they expresses the different years. So in this way, that we can see this seasonal pattern depends on the year or not. So you can see that all seasonal patterns are similar, but we have slight difference. For example, this year and this year. So the pattern is pretty similar, but this year is what? The 1950. In 1950, we have much more passengers during summer months. 1949, still the difference is not that huge. So we have slight difference in pattern. So if we don't have any, interaction effect, then these graphs should be parallel. Should be parallel if no interaction. So from this figure, we can maybe for this one, almost no interaction, but maybe slight interaction exists, we can say. So now that we want to develop tests for two-way layout with interaction. So we have basically the 3 quantities, alpha i's, and 3 sets of quantities, alpha i's and beta j's and gamma ij's. And we have m groups for the first factor, n groups for the second factor, and we have the q measurements for q repeated measurements for each pair of ij. So we can write in this way. So basically, we have m times n different pairs, right, for this question. And we have 1 parameter here, number of parameter. And we have the alpha I, but usually we set alpha 1 is equal to 0, or a summation of alpha I is equal to 0. But we have, in total, we have m parameters. Sometimes always we need 1 restriction, but the n parameters. And beta j, we have n parameters, and here m times n parameters. So actually, we only have m times n pairs. So this expression is redundant. We have 1 plus m plus n plus mn parameters to express, m times n levels. So something is redundant. So we have to set some restriction, such as summation of alpha I is equal to 0 and summation of beta j is equal to 0. So it reduces the number of free parameters smaller. it reduces the number of free parameters. And also we confine this condition, we impose this condition. So summation of gamma ij is equal to 0 for each j. Because the gamma ij will explain the difference of gamma ij's for specific j's. So gamma 1j and gamma 2j are relatively different. So we want to get that effect. So just relative difference is to be modeled. So we have to set the summation of this is equal to 0, or we set the one number, maybe January, as the baseline, something. So we need the condition gamma, the summation of summation over I of gamma ij is equal to 0. So this is for each j. So we have actually the n restrictions. And also for each I, the summation of gamma ij should be equal to 0. So yeah. So this is actually the m restrictions. So we have m plus n plus 2 restrictions. So originally we have the parameters. So okay, now we count the number of free parameters, independent parameters. So this is okay, so 1 plus m plus n plus mn, but we have restrictions 1 plus m plus n. And actually this becomes mn minus 1, so 1 smaller. And this happens because actually this condition, summation of gamma ij is equal to 0 for each j and for each I. So actually all of these conditions, one is redundant. Actually, if this condition is all satisfied and the second condition is satisfied from I is equal to 1 to m minus 1, the remaining condition is automatically satisfied. You know that the sum of all gamma ij is equal to 0. So that means the last condition is satisfied for I is equal to 1 to m minus 1. For I is equal to m, this condition is automatically satisfied. So actually the number of restriction is this minus 1. So this erases this one. So actually the total number of free parameters is mn. So it's a kind of annoying because we can just say xijk is equal to mu ij plus epsilon ijk, and it's done, right? So it's much easier to think about in this way. But our philosophy is that the mu or alpha i's or beta j's are more important and fundamental parameters, and we expect these are probably non-zero. But the interaction is more complicated relationship. So possibly these are 0. So that's why that we set up in this complicated way. And this is sample data. So factor 1, location. And factor 2, fertilizer. And location, we have 2 factors. So m is equal to 2. And the fertilizer, none or X or Y, so we have 3. So M is 2, N is 3, but we have 2 plants for each pair of this setting. So actually what's that? Last one is Q. So Q is equal to 2. So we have in total 12 observations. So yeah, so the number of free parameters is probably like this, alpha I, beta j, and plus gamma ij. So we have the one parameter here, and the alpha I is equal to 0 as baseline. Alpha 1 is equal to 0 as a baseline. So we only have alpha 2, so one parameter again. And the beta 1 is equal to 0. So we have beta 2 and beta 3. So that means we have 2 parameters here. And gamma ij, then we have some restrictions, but after several restrictions, we have the 2 additional parameters. So in total, we have 6 parameters. Actually, gamma ij, we have 6 parameters, but we have 5 restrictions and 1 redundant restriction. So 6 minus 4 plus 1. So 6 minus, we have 6 parameters. We have 5 restrictions and 1 redundant restriction. So we have 2. So 6 minus 5 plus 1. So we have 6 parameters plus epsilon ijk. So we have 12 observations. Sorry, the total number of observations, maybe I would say capital N. This is M and Q, so 12. So 12 observations and 6 parameters. So it's totally reasonable model. And we can make an interaction plot by this interaction, fertilizer, location, growth. So growth, we have multiple measurements. So we take the mean of growth. Then we can see this. So this is fertilizer and this is location. And depending on location, the effect of fertilizer is different. So for north exposure, the fertilizer X and Y have almost the same effect and much better than none. But for south location, the fertilizer X and Y have different effect. Y has much better yield, much better growth. And actually, the difference between no fertilizer and fertilizer X is slightly smaller. So it sounds like we have interaction effect. And here is the way to fit this. So growth is response variable, and the location is first factor, and fertilizer is the second factor. And the location times fertilizer, just we combine this. We multiply these two by this asterisk symbol. Then you get this. So this is effect of location. The north is baseline. So this is the effect of south minus north. So south is better. So you can see from this one. So south has larger yield. And fertilizer, none is the baseline because N comes earlier than X and Y. And actually X and Y has positive effect as well. And actually each effect have the standard error and the t-value and the test result. Actually test results are not really significant. It's natural because we only have 12 observations. And this is interaction term. So what's the effect of south and X? So what's the specific effect when we combine the south location and fertilizer X and location south and fertilizer Y? So location north is the baseline and the fertilizer none is the baseline. So the only possible interaction effects are these two. And you can see that the yield is lower if you combine the south and X. So basically, it can be interpreted as if it's in south, then yield, the growth is larger. And if we use X, growth is 3.5 additional 3.5 larger. But if we combine these two, actually we have to subtract 3. So the combined effect is 3.5 plus 3.5 minus 3. So the 4. So compared to the baseline, the south and X, that combination makes growth basically 4 higher because 3.5 plus 3.5 minus 3. Yeah, so interaction is -3. So so this combination may lower the yields. But anyway, so this is not significant. So maybe this happened just by chance. Yeah, most of today's quiz is to calculate either, maybe after this slide, we will discuss it. And this is the ANOVA test result. So LM1 is this interaction, so two-way ANOVA with interaction. And we test the location first and the fertilizer second. Actually, it's exchangeable if it's balanced data. I mean, just we have same number of observations for each IJs. Actually, we can change it. And this is the interaction term, so location and fertilizer. I think this is probably not interchangeable, but usually we don't. Anyway, that we consider the interaction at the end. And we calculate the sum of square. Yeah, actually, we haven't discussed how to calculate these numbers, but in the same way, almost in a similar way as two-way ANOVA, we can calculate these sum of squares, and we have f values, and we get whether or not these are significant. And actually, in this case, nothing is significant. One reason is we only have 12 observations. And another reason is that we put maybe too many factors, too many explanatory variables for a small data set. So that may be another reason. Yeah. So that's it for two-way ANOVA with interaction. So again, if you want to consider interaction, that we need multiple measurements for the same pair of IJ. Okay, so the next topic is unbalanced data. So when the number of measurements for pairs of the treatment, I mean the pairs of groups is different. So Q is the number of observations for each group, but the Q is not constant for IJ. So in this case, we can still fit the model and do ANOVA, but the table has to be interpreted sequentially. So the ANOVA table, we can generally exchange the order of two factors, but in unbalanced case, so if Q is different depending on pair of IJ, we have to have specific order. So the line for the predictor one, the first predictor tests the significance of alpha i's, but the second predictor line for the second predictor tests significance of this second factor after accounting for the first factor. So sometimes if location is adjusted, the fertilizer doesn't make any difference. So that kind of test is done in the second line. And we omit the ANOVA table for this specific ANOVA formula for this specific case. Because anyway, we use more generalized form. We use the linear regression form to extend this kind of table. So basically, yeah, so maybe I have to discuss that. So linear regression, we have only discussed simple linear regression. But if we allow the multiple predictors in linear regression, so multilinear regression, that is more general than ANOVA. So if we just develop the very general theory for multiple linear regression, then actually it includes all ANOVA analysis. So actually for complicated case that we don't really define SSD or something, then we directly use the more general result to define this ANOVA table. Okay, but still that we do some examples. And the MT-CARS dataset includes the MPG, the mile per gallon, of 32 cars by the number of gears and the number of carburetors. I don't know really about what is the carburetors, but basically we have two specs for each model, and the number of gears, 4, maybe 4 or 5, or no 5, actually the 1 or 2. the gears 3 or 4 or 5, and the number of carburetors, that is 1 or 2 or 3 or 4 or 6 or 8. And this is contingency table. Okay, so the number of observations. We have 3 cars with 3 gears and 1 carburetor, or we have actually no observations with 5 gears and 3 carburetors. So we have entirely different numbers here. And in total, we have 32 observations. Actually, the first line, we have 15 observations, 12 and the 5. So in total, 32 observations. But the we have different numbers in this table. And we want to fit the MPG on gear and carburetor, but we have to make it as factor vectors because it looks like these are numeric values. So we make it as factor. Maybe in a homework, you have to do, in a quizzes, you have to make some vectors into factor vectors. And we can fit the linear model, MPG on gear and carburetor. So gear is the first predictor, carburetor is the second predictor. So ANOVA table here, so it tests if the gear is significant against null model. And we test if carburetor also matters for MPG, even after accounting for the number of gears. So that p-value is also very small here. So that is how to read this table. And if we change the order of these 2 variables, we get this table. So yeah, so this has been changed. But you can see that these numbers has been changed. You can maybe see the just p-values. So this is the 1.3 times 10 to the power negative 5 and 3.1 times 10 to the power negative 6. So these are different from these because order has been changed. Maybe you can focus on the carburetor here. So this p-value, 4.7 times 10 to the power negative 5. Here, 1.3 times negative 0.5. So this is smaller than previous page. Why? Because, if we don't have information of gear, the information of carburetor becomes more important. So the p-value should be lower, more significant. So actually, everything can happen for the real data set. So not always lower, but the most of the time it's lower, I would say. Sometimes if you combine 2 variables, then each of those 2 variables makes more sense. That's possible. So it's not necessarily always true, but generally, if we put the variable in the earlier order, then p-value is more significant. P-value is smaller. Yeah, so again, we test we test the equation 6 against 7 and the equation 7 against 8. Yeah, and actually so the next slide discusses how to calculate the ANOVA table. And if we have these 3 models, at least we can calculate SS residual for this model and SS residual for this model and sum of squared residuals for this model. So we have 3 quantities. And actually these quantities determines SSD gear and SSD carburetor and SSD residual. Yeah, so this is actually the definitions of SSD when we have, unbalanced data. And SSR0 minus SSR1 is actually 483 if you fit those 2 one-way, the ANOVA models. And the SSR1 minus SSR2 is 425 and so on. And actually these numbers are the same as so these are obtained by this. you can use the linear model, and we get the error residual part, and take sum of squares, then we get these numbers. And these numbers are actually, these numbers actually are the same as the numbers in ANOVA table. So here. So actually this table is made in that way. Yeah, and actually this works in the same way. So we have the degrees of freedom here. So if we divide this number by degrees of freedom, we get the mean squared deviation, and also the carburetor. 425 divided by 5 is 85. And the last one, it's the same thing. And the F value is the ratio of MSD divided by this MSD. Then this F statistic follows the F distribution with degrees of freedom 2 and 24, because 2 and 24. And then we can calculate this p-value. So almost that we can do in the same way. Yeah, and exercise 5, the Johnson data. Johnson and Johnson's data set. This is quarterly profit of Johnson and Johnson for 21 years. And then you can make the year and the quarter effect. And you can check the interaction by interaction plot. Then you can do two-way ANOVA and get whether each term is significant. Exercise 6 is actually the same as the example we discussed right now. So we have empty cars dataset. We have 32 cars, but here we explain MPG by the number of cylinders and the number of gears, slightly different. And then you are supposed to do the two-way analysis of variance. And you can get the which variables are significant, and also we can see how much variability is explained by the number of cylinders or the number of gears. Okay, so what time? 45. Okay. And yeah, I would like to finish this slide. So we have discussed t-test. So under normality assumption, assumptions that we did the t-test for 2 groups, and the multiple groups ANOVA. So this is the 1 factor and the 2 groups, and the 1 factor and the more than 2 groups is the ANOVA, and the 2 factors and any groups. That is the two-way ANOVA. So this is maybe one-way ANOVA, I would say. One-way ANOVA and a two-way ANOVA. And how about the non-parametric version without assuming normality? Then 1 factor, 2 groups, the Wilcoxon rank sum test. And the 1 factor more than 2 groups, then Kruskal-Wallis test. And we have maybe only one L. And we have the two-way ANOVA version of Kruskal-Wallis test. So that is called Friedman's test. But we don't really discuss this in this lecture. So you can search for it. Yeah, so that's it for today. And yeah, that's it for today. So see you next Tuesday.